So we're going to talk for just a second here about orthogonal trajectories. And I encourage you to read more about this in your section in the book. But an orthogonal trajectory of a family of curves is a curve that intersects each curve at right angles. So it goes through the whole family of curves and it intersects every single curve at a right angle. And it's useful when we're dealing with problems with electric potential, hydrodynamics, and heat flow problems. So what we're going to do here is we're going to find the orthogonal trajectories of the family of curves x, y equals a. And in this case, a represents an arbitrary constant not equal to 0. And so what does that mean? That's kind of like saying y equals a over x, which is like a rational function. Y equals 1 over x. A is any number, it just can't be 0. So in order for us to do this, our first step will be to differentiate implicitly. So I'm going to take the derivative with respect to x of xy equals a. And so doing that, I have to use the product rule on the left. That gives me x dy dx plus y times 1 equals the derivative of that constant a is 0. Which we can rearrange a little bit and say that dy dx equals negative y over x. So just using some algebra, dy dx is negative y over x. So what this is the slope of the tangent line at any point xy on one of the graphs of xy equals a, these hyperbolic shapes. The slope is going to be y prime equals negative y over x. So I've typed that, what I just said, and rewritten it here. The slope of the tangent line, that's what the derivative represents, at any xy point on one of those original hyperbolas we started with, xy equals a, or rather y equals a over x, is going to be given by this derivative y prime equals negative y divided by x. So one thing to keep in mind, orthogonal means perpendicular. And when we're dealing with perpendicular equations have negative reciprocal slope. And something else what we know, or that we know, is that these orthogonal trajectories, they must satisfy the differential equation, which is dy dx equals positive x over y. Because in order to be perpendicular, you're going to need that negative reciprocal slope. So at this point, we're going to solve a separable differential equation. So we'll take this equation, and that's the same as writing y dy equals x dx. We can integrate on both sides. The integral of y dy equals the integral of x dx. Integrating both of those, we get 1/2 y squared equals 1/2 x squared plus c. And I can multiply through by 2 just to clean it up a little bit. Y squared equals x squared plus 2c, or y squared minus x squared equals 2c. And in this case, with that 2c, we're just going to call it b, some other arbitrary constant. So y squared minus x squared equals b, and that is just where b equals 2c. And so I've grabbed and I brought in here a picture from your text. It's hard to make it fit in the space that I have left. But the blue curves represent that original rational function we started with, y equals a over x. So depending on what your a value is, y equals 3 over x, y equals 2 over x, y equals negative 5 over x, you're going to get a rational function that's hyperbolic in opposite corners. And the red curve represents the different hyperbolas we could get opening to the left and right or up and down, depending on what our b value is. And you'll notice at all the points, anywhere one of these red lines intersects the blue lines, you're going to have right angles. And so each line has its own orthogonal curve, and we have these two families of curves.